Hi, I'm Mike Swanbaum, and today I'd like to show you how you can find the principal stresses associated with a three-dimensional stress state, as well as the unit vector in the direction of one of those principal stresses. And I'm going to do all this using a Casio fx-115es Plus calculator, which is the calculator that a lot of people use for the FE exam and the PE exam, since it's an approved calculator for that purpose. So let's get started. So first of all, what we see in the upper right hand corner up there is the stress state that we would like to try to work with. That stress state, first what we're going to do is find the stress invariants for that stress state. Those stress invariants are going to feed into a cubic equation, which we can solve for the principal stresses, and from there we will work with a linear system of equations in order to figure out what the directions are. So here's the calculator. I've got an emulator up here that we can see what all the keystrokes are going to be. So the first thing I'm going to do is load these stress invariants, and so what I have here is I'll have the normal components of stress, which will be the 22, we have minus 7, and we have minus 17. That takes care of the first stress invariant, and I'm actually going to store that into variable A. Okay, so what we've got here now is we've got that much is done. Okay, the next one is a little bit more complicated. I have to take each pair of normal stress components and multiply each of them by each other and add all those together, then subtract off the three shearing stress components squared. So we'll start entering that. So what I'll have is 22 times negative 7 plus negative 7 times negative 17 plus 22 times negative 17 minus 12 squared minus 15 squared minus 3 squared. And we will enter all of that in there, which gives me negative 787, and I'm going to store that into variable B. Okay, so just to kind of keep track here, so far what I've done is I've taken this and stored it into variable A, and I've stored this into variable B. Okay, so the next step is really slick. It's because this calculator has the ability to calculate determinants, and so we can take this 3x3 matrix that has these stresses in it and calculate a determinant, which is really, really nice. To do that, what we want to do is go into matrix mode. When we do that, it's going to prompt us to enter some information for one of the matrices that it will store. We're going to store this into matrix A. It will be a 3x3 matrix, and we just need to enter the values of this stress tensor in here. So we have 22, 12, negative 15. Here we will have 12 again. Then we will have negative 7. And we will have 3. Over here we'll have negative 15. Then we will have 3 again. And here we'll have negative 17. And this next keystroke is probably the least intuitive on this calculator, because once you've entered all this stuff in, it doesn't feel like you want to hit AC it feels like you're going to erase it all or something. But that's the keystroke that you make, is AC, to get into the general sort of matrix mode. From there we can hit Shift, and above the 4 key you'll see that it basically gives us this option of having some matrix functions. And what we're going to do is we're going to choose 7 for determinant, and then we are going to go back into that same menu and pick matrix A. And you see there that the result, that's something that would have taken a bit of effort for us to do if we were doing this by hand, and that was fairly simple. So I'm going to take that result and store it into variable C. Okay, and just to kind of keep track of that, I'll put that over here and say that this is now going to be in variable C. All right. So now I have each of these variables stored into A, B, and C. So what I can do is pull up this calculator again, and we can go into a different mode. In the equation mode, you'll see there number 5 mode. It gives us several different types of equations that can be solved, and one of those types of equations is a cubic equation, which is this option number 4. What we have to enter here are the coefficients for the cubic equation, where all of the terms are going to be to the left side and there will be a 0 to the right side. So what we have here is that we'll have a coefficient of 1 that's associated with the cubed term. We'll have a coefficient that is the first stress invariant. We actually need to take a minus before we put the value in here for that first stress invariant that we have stored in A. And then for the next one, we do not use a minus sign. We just store, or we put in there what we have stored in variable B. And then we have in the last term negative the variable we have stored in C. Once we have all of these put in here, we can hit equals, and it will actually give us all of our stresses. And so one of those stresses is given here first. It is 30.084. I'm actually going to write these down because there's not a great way that I have discovered in this calculator to save these results so that we can use them later. So I'm actually going to just write these down. 30.08477. .043. And that would be in KSI. Okay, well, we may as well write these other ones down too while we're here. We'll have a negative 7.1488. .38627. That will also be in KSI. And then lastly, we will have negative 24.9359. .318. That's also in KSI. And these variables that we have just found here, these are the principal stresses associated with this three-dimensional stress state. These are the stresses that exist on planes where there will not be any shearing stresses that will also be present on those planes, which is a pretty neat idea. All right, so that's the first starting point here of this problem. And I didn't really mention it before, but I have drawn over here a cube that has all these different stresses applied to it, and rather than show them with negative signs, I actually went ahead and showed each of those stresses applied the direction that it really would be applied, that is implied by the signs that are included in the original stress tensor, assuming that you're going to use standard sign notation or standard convention here. All right, so what's next is we actually have to find a unit vector that is applied in the direction of the most positive of these principal stresses. And actually the process would be the same if we wanted to know the unit vectors in the direction of the other two stresses as well, but we're going to focus on just one because otherwise it would probably get kind of boring. So we are going to focus here on just the most positive value of principal stress. So what I'd like to do is take that value and actually store it into another variable here. I'm going to use the variable d. And to do that, since there's not a great way to just do it directly in this calculator, I'm going to go back to comp mode and enter this variable 30.08477043. I think I've got that entered right. And we're going to store this now into variable d. All right, so the next step of this equation involves using this system of equations that we came up with earlier in the derivation, which was in another presentation. We need to use the system of equations that we have down here where I've labeled them equilibrium equations for this element when it's aligned with a principal direction. The only problem with this is that these equations that we have here are not all mutually independent. So there's going to be an equation that is a linear combination of the other equations, which means that if we try to solve it, we aren't really going to get this actual solution. There is a way around that, though, and the way around it is this. So ultimately, we want a unit vector that acts in this direction, but we're okay if we get any kind of a vector that acts in that direction, and the easiest way to get that is to replace one of these three equations. So I'm going to go down here and eliminate one of these equations. Say we're not going to do that last equation there. We're going to do an alternate one instead. What this functionally does, and I'll show you the equation we'll put in there instead. We're going to put in a row where we basically have 0, 0, 1, and 1. What we are functionally doing there is just manually setting the component here that goes in the z direction equal to 1. When we do this, what will come out of the rest of this equation are values for lambda x and lambda y that are proportional to this value of 1. So they'll be in the correct proportion to lambda z, where we assume lambda z is equal to 1. And what we can do then is once we get what those values would be of lambda x and lambda y, assuming that the value of lambda z is 1, we can actually go back in and divide by the overall length that is implied by each of those values, and we'll get to that in just a second. So this is actually not hard to do because the calculator has a solver for a 3x3 linear system, and so we're just going to go ahead and enter that in the calculator. So to do that, we go to mode. Again, we go to 5, which is the equation mode. And under there, you'll see that option 2 is the 3x3 system. So we will enter into this 3x3 system. Remember, we stored that value for stress, which is this sigma p value that I had over here. We will put in that value and subtract off what was in that position in the original stress tensor, which was 22. Okay. Next, you'll notice we have negative tau xy, so that would be negative 12. Then we have, it started out negative 15, and we have, you have to negate that again, so it becomes positive 15. And then lastly, we have 0 in that row. Then we will have negative 12. We will then have what was stored in D minus, and then we have to look and see what the normal stress was in the y direction. It started out as negative 7 ksi, so we'll subtract a negative 7 from that. And then the next one there would be a negative tau sub yz. Tau sub yz was 3, so we put in negative 3. And that last row is 0. And then in this next row here, we just put in 0, 0, 1, 1. And we solve. Now, this is another spot where I don't have a great way of taking these results and getting them automatically stored into one of my variables that's in the calculator. So I'm going to go ahead and write these down. And so I'll basically write this down as x being negative 3.3388. Then I have 86931. And we'll hit equals again here to give our next solution for this system of equations. And I'll take that value and I'll write it down on the page here because we're going to need to store that into another variable. So that value is negative 0.955 excuse me, 9995 1119 39. And of course, the last value in that system that we found was z, which is 1, which is because we set it to 1. So we'll write that one down last. All right, now what we want to do is in the calculator there, we want to switch into comp mode again so that we can store these values that we just found into some variables. So what we'll do is we'll enter that first one. We'll go negative 3.33.8886931. I'm going to store that into the x variable. Next, I'll put in negative 0.9995 111939. And I'm going to store that value into the y variable. And then our last one, of course, is 1, so I don't think I need to necessarily store that into any variables. So the last step of this process is to take these values, and what these values represent are essentially components of a vector that is not a unit vector, but is pointing in the correct direction. And so we're going to take these and now normalize them down to a unit vector. And the way we do that is first we figure out what would the overall length be of a vector that has these components. So to do that, I need to take the square root of what I have stored in x squared plus what I have stored in y squared plus 1 squared, 1 being the length of the z component for this non-unit vector that's in the right direction. All right, so the value I get out of this, let me store that into my m variable. All right, and I'm just going to make a note of that right here. The length of this vector I've stored into my m variable. All right, so now what we want to do is take each of these components and divide by the overall length in order to get the components of a unit vector that points in the direction that we're interested in. All right, so what I'll do here is I'll take my x variable and divide by what I have in my m variable. And this gives me negative 0.9208. Which is enough precision for what I'm interested in here. The y component that we have, we will take what we have stored in y and divide by what I have stored in m. And that gives me negative 0.2757, we'll say. And then the last component that we have here would be 1 divided by what I have stored in my m variable. 1 because that's the length of the component of this non-unit vector that we just found because we set it that way. So this gives us 0.2758. So that's how we figure out the components of a vector that points in the direction of the first principal stress there, the one that has a magnitude of 30.08477 or so. If we wanted, on the other hand, to figure out what one of the other of these principal stresses, what direction one of those other principal stresses went, we could take another one of these values here, like the negative 7.14, for instance, and then plug it in to the principal stress variable that I have in this equation. Or if we wanted to get the last one, we could get that last, the direction of that last principal stress there by taking that and plugging it in again for sigma sub p, and then chasing the rest of the solution through from that point. So I hope that this has been a valuable lesson, and I think that this is definitely a useful thing for people to know how to do to get your principal stresses out of a general three-dimensional state of stress. Thank you for watching.